Okay, we'd like to welcome everybody here this afternoon for our latest celebration. If you'd like to take your seats right now, the food will be there afterwards, and then we can get started. We are focused this afternoon on Professor Michael Harris. This program, the Celebration of Faculty Careers, was actually started by the college a couple of years ago, and it gives the opportunity for individual faculty to sort of reflect back over their careers and sort of see the directions that they may be headed into the future, or what might be intriguing for them to start anew. So this afternoon, Dr. Harris is going to be looking over his research career. But I'd first like to say a few words to introduce him for anyone who doesn't have all of his background. So Mike Harris now is the Associate Dean for Engagement and Undergraduate Education, as well as the Reilly Professor of Chemical Engineering and Professor of Environmental and Ecological Engineering in the college on the West Lafayette campus. He was actually a Purdue University faculty scholar from 2002 to 2007 and served as programming chair and chair of the ASEE Minority Division from 2011 to 2014. He was named a fellow of AICHE in 2009, and he won the AICHE Grimes Award for Excellence in Chemical Engineering in 2005, and the AICHE Minority Affairs Distinguished Service Award in 2009. So he's been a busy guy. He's the author of 97 peer-reviewed publications and 11 patents. He actually, going back, he received his BS in Chemical Engineering from Mississippi State and both his MS and PhD degrees in Chemical Engineering from the University of Cincinnati. Dr. Harris's research is in the area of nanomaterials, colloids and interfacial phenomena, transport phenomena, particle science and technology, microwave sensing of pharmaceutical powders, solidification of drug excipient matrices, environmental control technology, and electrodispersion precipitation processes. So today he's going to take us back a bit to a particular aspect of his research activities of which he's particularly fond. Dr. Harris.
Thank you. I hope you can hear me. I think and I think my voice is loud enough to be heard without a mic. So let's see how this goes. So today I'll talk about metal-coated biotemplates and particle deposition during evaporation. And first, I'll start off by giving a brief overview of my research projects that I've had in the past that actually led to me getting to the point where I'm looking at these biotemplates and looking at drop evaporation. Before I get started, I would like to show you this quote from, I think it was the 100th centennial celebration for the department. And this was the description that a man of great wisdom, Phil Onecat, put in there about me. He said, first he said that I was, first of all, shown with another professor from engineering education. The next thing he says is that he's interested in everything. And if you heard the description of my research areas, that kind of summed it up. I do have kind of high interest in many things. And the last thing he said is that I'm unable to say no, and therefore I ended up being the Associate Dean for Undergraduate Education. I also was not able to say no and ended up giving this presentation today, so yeah. So here's a brief outline of the presentation. I'll give you a brief historical overview of research activities, some of the research activities that have occurred in my group. Then I'll give you two more in-depth presentations, one on metal-coated biotemplates, and the other on particle deposition during drop evaporation. These are some projects that we're currently working on and have worked on for a little while. And then the last thing that I'll talk about is my future fund or future research projects. As a matter of fact, given the title of this presentation, I almost decided to call it Having Great Fun, because that's the way I view my research career. So the first thing that I want to talk about is the dynamics of nanophase formation and growth. And this is the creation of nanosols. In particular, I'm looking at the formation of silica nanoparticles from tetraethyl orthosilicate and carrying out that reaction under basic conditions in an alcohol. The researchers that worked with me to contribute on this was David Green, one of my former graduate students, and Hassan Bakari, a postdoc who had math skills that were out of this world. And my math skills are still in this world. But we worked on this from about 1996 until 2003. And one of the questions that was asked is, how do these nanoparticles, these very monodisperse nanosilica particles form and grow? And there was a debate, one where one group said that very small particles, 1 to 2 nanometer particles formed, and then they would aggregate to form these very nice looking particles. And they are beauties, they really are. Every time I see these particles, I get emotional. Now, oh, I'm supposed to behave myself. So, I'm sorry. And another group used cryo-TEM to show that the first particles were about 20 nanometers in diameter. And so that debate kind of went on for a while, and then I came on the scene and decided, well, let's look at the hydrolysis of the TEOS and condensation of the TEOS and see what species we can detect using 29 NMR. And what we found is, sure enough, what you see is the unhydrolyzed This is a another disappearance of the TEOS. You can also see the first hydrolyzed monomer increases and then kind of decrease somewhat, and then we of particle formation. So using small electron scattering to look at the particle growth as well as looking at the slope of the velocity, it tells you something about whether or not the particle is kind of a fluffy type of object that's doesn't have extremely high density to where it goes all the way up to 4 in the case of methanol. And at that particular point, you have a spherical particle that has a smooth surface and where it's a solid. So these were some of the things we were able to get from the small electric scatter. So the cryo-TEM particle was kind of a low-density particle, and sure enough, X-ray scattering also showed that indeed the particle is a low-density particle that densified over time. gyration. And these are some data showing the first particle that appears in ethanol, the first particle that appears in methanol, where the particle is bigger, almost twice the size of the first particle that's coming out in methanol. And then the other data are small dynamic light scattering results that measure hydrodynamic radius. And if you look at the data, the dynamic light scattering and the small X-ray scattering results are consistent. So we answered that question of looking at the first particle. It was a very small nanometric particle, 1-2 nanometer particle, whether or not it was a 10 nanometer we were able to answer that question, who's right? The first person talked about the very small particles or the cryo-TEM work was correct. And so we were able to also use to look at the particle size and scattering. So as you can see, this work was done some years ago, almost 20 years ago. Next thing I looked at was these metal alkoxides that are very fast reactions. And what I decided to do is to use rapid mixing techniques and continuous flow through experiments to measure the kinetics of the hydrolysis and condensation of these reactions. And once again, you have the hydrolysis reaction, and you also have the condensation reactions where you can have either water, where you release water or you release the alcohol. So, in a lot of papers I read, and look at the hydrolysis and condensation kinetics, they use gel time measurements to say something about the hydrolysis and condensation reaction. Well, that's a pretty technique for doing this. And I wanted to get a better picture of the removal of the hydrolysis reaction and also and small angle X-ray scattering. So this is a simple technique that I use where we have a solution of alkoxide and solvent and hydrosolvent and water and solvent. Also sometimes we put an acid in this system over here and mix these two in a mixing tea and then allow it to flow, allow either do the FTIR measurement or the small angle X-ray scattering measurement some distance away from the mixing tea. And with that, you can get kinetic information. So these are the data that we're able to get. So we're able to take our first measurement at about 80 milliseconds. And we're looking at the water remaining in the reaction divided by the initial concentration of water, and that quickly dropped to about 0.8 in about 80 milliseconds. And then the alkoxide group, about 60% of the alkoxide groups were removed with that first 80 minutes as well. And so what I show over here, basically, what happens if you do the first hydrolysis, how much water, what the water ratio should be, 0.91, and if two water molecules are reacting with the alkoxide, how much water should remain, and so forth, all the way until if all four water molecules if all four of the alkoxide groups are hydrolyzed. One of the issues is typically the first couple of hydroxyl groups can come off very quickly, but the others are a little bit stubborn, and so they don't come off as fast. But what this shows is for zirconium alkoxide, in this case it's zirconium butoxide, you see a very fast hydrolysis, and you see where probably 90+% of the alkoxy groups are removed. If you look at the water, you see that the water basically stays about the same, which means that initially you get a very fast hydrolysis of the first two alkoxy groups, but then later on you have the condensation, the alcohol producing condensation reaction occurring. We also looked at titanium ethoxide and looked at that, how that concentration varied both the water, shown here, and the titanium alkoxy ligand. And as you can see, it does not decrease as quickly as the zirconium alkoxide. And you can also see that the water continuously decreases, showing that you still have some hydrolysis occurring as well as condensation occurring in this particular system. And this slide just shows what happens if you look at the FTIR data for the alkoxy groups and how they decrease over time. And then you look at the radius of gyration from data you get from small and X-ray scattering. And what you see is these particles start growing very quickly. And so using this particular technique, you should be able to get a better picture of the hydrolysis and condensation kinetics for these particular systems. So the conclusion from this work is that, yes, we were able to look at the zirconium and titanium alkoxide reactions, although they were fast, using this rapid mixing flow-through technique. And also, if you look at the hydrolysis of zirconium relative to titanium, zirconium hydrolyzed much faster and more completely than the titanium alkoxide. And so, I forgot to say very quickly, but the individuals who helped with this project were two postdocs, Singhal and Look, and the final individual was an undergrad researcher that worked with me. And this work was actually done when I was at the Oak Ridge National Laboratory. The next topic I would like to talk about very briefly are some additional research activities that we did in my research group. One was part of the Engineering Research Center that Rex was over. It was the one research area was the developing microwave sensors for moisture content and bulk density measurements of pharmaceutical powders, for both static powders as well as flowing powders. And several publications came out of that. As you can see, that work was done between 2006 and 2015. And then we did drop printing of pharmaceutical from solutions of polymers and solvents, as well as dissolving the pharmaceutical in melts and then looking at the crystallization and the dissolution of the drugs. This work was done between the years 2006 and 2015. And the final thing that I worked on from this list is the electrodispersion precipitation process, where we were interested in making hydrous metal oxides and also calcium alginate microspheres, where these calcium alginate microspheres were used to encapsulate proteins. And this work was done between 1995 and 2009. Now, the two major items I want to talk about to wrap up this presentation, and that means we'll all be here for another 50 to 60 hours, so get comfortable. Metal-coated biotemplates. This research was done by several of my graduate students, former graduate students, Sung-Yup Lee, Liz Royston, Lem, Freer, and is currently being done by Mayo Patagon. There are 2 undergraduate students who are working on the project, or have or are working on the project, Gloria Novikova and Aaron Retzloff-Roberts. This work has been going on since about 1999, while I was still at the University of Maryland. This is when this project first started. And Sung-Yup Lee actually started on this project with me at Maryland and transferred here when I came to Purdue. And I guess his famous quote on this project was, "I hate TMV." But he actually did some very nice work, because early on he encountered a number of obstacles, but eventually was able to overcome them and publish some nice papers. So what is tobacco mosaic virus? Well, tobacco mosaic virus is what I would say is a biotemplate for my research that's about 300 nanometers in length, 18 nanometers in diameter, on the outside diameter, and it has an inner core that's about 4 nanometers in diameter. And researchers have coated TMV with metals on the exterior surface as well as in the interior surface. TMV, the reason why it's such an excellent template is that it was first discovered in 1880, so if it was discovered that length of time ago, you would think we would know a lot about it. It's easy to grow. I mean, you can make 1 kilogram or harvest 1 kilogram to perhaps 2 kilograms of purified TMV per acre of land. The particles are very monodisperse, and they form nanotubes, as you can see. The virus is also stable because it stays intact in a pH range from 2 to 10, and temperatures below, up to, I should say, 90 degrees Celsius. So that means that you can carry out a number of different chemistries using TMV. And with genetic engineering, you can make TMV, have it be stable even in, for some organic matrices. We primarily use it in water and in some cases alcohol water systems, but primarily in aqueous solutions. So the genetic engineering, you're basically adding more cysteine groups on the surface. In our case, you're adding more cysteine groups on the surface of the TMV so that you can have great affinity for certain metals. He says, so why do we want to do this? One application that I asked one of the grad students, Liz Royston, is she would, if she could anchor the TMV on a substrate, and so she was able to anchor the TMV on a gold substrate. And what happens is the TMV tends to stick straight up, and only one end of the TMV will be anchored to the substrate. And then you can coat the TMV with palladium, and then after you coat it with palladium metal, then you can coat it with, you can reduce metals such as nickel and cobalt on the palladium. And one of the applications for that was in making high surface area electrodes that can be used in batteries, and what you find is that the battery has greater charging capacity with this porous surface for the electrode. We also use it for detecting hydrogen, the second item here. I gave a presentation at the ASHE meeting, and this professor here, he asked me if I could send him some of these palladium-coated TMV, and he put it on an acoustic wave device and was able to detect hydrogen, because the palladium would absorb the hydrogen, produce palladium hydride, and in the presence of hydrogen, in the absence of hydrogen, it would release hydrogen from the palladium hydride, and so you have a swelling and contraction of the palladium, which was very good because a lot of palladium sensors were a thin film of palladium on a substrate, and if the hydrogen absorbed from the palladium would swell, and if you remove the hydrogen from the environment, the palladium will desorb, and the palladium would shrink, and what happens is eventually the palladium would crack, and the sensor would fail. But in the case of these small nanoparticles, the palladium could absorb and swell and shrink, swell, shrink. You can circulate the hydrogen environment millions of times without failure of the device. So those are two applications for TMV, and there are probably millions of others that we hadn't thought about and that people are currently doing. But in addition to palladium, there were other metals that we've coated. This is the palladium-coated TMV, and this would be platinum-coated TMV, and this is gold-coated TMV. Now, all of this looks great. And early on, what we were doing, we were using an external reducing agent. And the external reducing agent, if you put that in and you have palladium metal that's not adsorbed onto the surface of the TMV, the reducing agent would reduce the palladium in solution. It would also reduce the palladium that absorbed onto the surface of the biotemplate. And what I noticed is that we would have some material that was coated with palladium, some material that was not coated with palladium. And that was a very inefficient use of the palladium. So we decided to look at the palladium in greater detail. And as I said earlier, there are two methods. One, where you use a reducing agent, and some of the reducing agents are like sodium borohydride, sodium hypophosphate, and dimethylamine borane. So we can use any of these to reduce the metals. And as I said, the coatings weren't always uniform and so forth when we did that. So you end up with coatings that look somewhat like this on some of the viruses, but not necessarily all of the viruses. So one of my former students, Lim, noticed that the palladium would reduce on the surface of silica particles when the particles were heated at 50 degrees silica. These were silica particles that were functionalized with either amine, thiol, or carboxylate groups. And so he decided to try the technique with just TMV and palladium, and just heating the solution to a high temperature, in this case 50 degrees C, to see what happens. And what we discovered is that every single TMV was uniformly covered by palladium. And so the plant virus behaved as a some type of reducing agent for the palladium ions. Well, we said, well, what happens if we do multiple coatings? Can we make thicker coatings? And sure enough, we went from 1 coat to 6 coats of the palladium, and down here, Alex Freer showed that as you increase the coating, the diameter thickness of the palladium on the surface of the TMV increased as shown here. And this was confirmed by both small angle X-ray scattering and transmission electron microscopy. But we still don't understand this whole palladium reduction, and we collaborated with Jeff Miller because he was doing X-ray absorption spectroscopy, so we could actually look at the reduction kinetics of the palladium ion. And we also use UV-Vis experiments, because UV-Vis experiment, we have an UV-Vis instrument here, and it's not that expensive to use. But this is the reactor that we use, which also is one of Jeff Miller's reactors, where we could put our solution in there and stir it, as well as control the temperature. And it only holds 3 milliliters, but that's enough for us to get some good data. And this just shows you the procedure. I won't go through that here. But here are the results. And using UV-Vis spectrophotometer, we had an initial solution of 0.75 millimolar palladium and 0.022 milligrams per milliliter of TMV. The initial solution was here at level 2, and this axis here is log 100 times the palladium ion concentration at time t divided by the initial palladium concentration. And you see this big drop in the first couple of minutes doing the reaction, but afterwards there was this kind of first order reaction kinetics exhibited by the reduction of the palladium. So, and these are the rate constants that we got from 2.2 hours to the minus 1 inverse hours per milligram of virus, because we try to normalize by the amount of virus we had in there, because the rate constant tended to increase as a linear function of the mass of the virus. And so we showed the wild type TMV for 1 cis TMV and for 2 cis TMV, 1 cis, 2 cis. As you can see, going from wild type to 1 cis, the rate constant was 3.2. However, for 2 cis, it remained at 3.2. And so these are the last two of the genetically engineered wild type TMV. And looking at the activation energy, we got an activation energy of about 43 kilojoules, which is consistent with the literature for DMAB type of reduction. And what exactly does that mean? Right now, we aren't really sure. So that was for UV-Vis. So how do kinetic constants compare with X-ray absorption spectroscopy? And here is the cell that was used for carrying out those measurements. Once again, this is work that was done with Jeff Miller. And as you can see, for X-ray absorption spectroscopy experiments, we get the same type of first order kinetics. And I should say that for the UV-Vis, we were looking at the disappearance of the palladium ion, not knowing if it was converted to palladium metal or not. So the only way we can know if it's converted to palladium metal is either by looking at the particles and looking at probably high resolution TEM or some type of XRD, or by using this X-ray absorption spectroscopy method. And this method shows that yes, the material is being converted to palladium. You are getting production of the palladium ion into palladium metal. Now, we did have to go to higher concentrations of palladium and TMV for the X-ray absorption spectroscopy experiment. But if you look at the rate constant, for wild type it was 2.7, for 1cis 3.2, and for, in this case, BSMV, which is another virus, which had about the same rate constant as the 1cis TMV. So once again, we observed first order reaction kinetics, and the rate constants well, I think I must have removed one of my things. But the rate constants that were observed for using UV-Vis were very consistent with the rate constants that we got using X-ray absorption spectroscopy. However, one of the things that we noticed was this, as we said, this very quick drop in the palladium concentration within about 2 minutes. That probably indicated that some type of absorption, palladium was absorbing into the surface of the TMV, because in the UV-Vis experiment, we have to filter out the palladium. And you have to filter out the TMV. And if we're filtering out the TMV, then any palladium that's absorbed from the TMV will be filtered out as well, even before it starts to reduce. So we looked at the absorption of palladium on TMV, and this is the loading of material on TMV, 127.3 moles of palladium per kilogram of TMV. And you primarily get kind of a linear isotherm type of behavior, but in some cases you get a privileged isotherm effect. So, yes, you get and when we look at the absorption capacity on palladium on the TMV, that's not reactive, just a palladium ion, it's absorbed on the TMV, we can look at that, and it does indicate that the first data point should probably be somewhere about 1.8 to about 1.7. That first data point, if you look at the amount of palladium that's absorbed on the TMV. So that was encouraging, but it also shows that there is some reaction that's probably occurring that's causing that drop as well. It's not just due to absorption. Now, we also want to look at the particles that are growing on the surface of the TMV. And so we use small X-ray scattering. As you can see, I'm going back to small X-ray scattering over and over again. I started with the first set of experiments I did before coming to Purdue, even when I was at Oak Ridge National Laboratory. And also using some type of spectroscopic technique in order to monitor the reaction of material, reaction kinetics. So, here we use small X-ray scattering, where we have a quartz tube, and then incident radiation goes through the tube, sampled in the tube, and you get scattering, and you get a scattering pattern that looks something like this, and you see it varies as a function of time, especially if you look down here, where you have a nice deviating region, so that you can get the size of the particle, and the model that, and this is Mayo's work that he used to model this, the data. There's like a second level Guigné region. Exactly what those particles are, I couldn't tell you, but the small particles are probably the very small particles that we see on the surface of the TMV. There's also some question, well, could these also be the pore spaces between the particles? But I think it's probably the very small particles that are on the surface of the TMV. But this second level growth, we haven't figured out exactly what that is. So, in terms of TMV, if we go from the wild type TMV to the 2-cis, TMV 2-cis, I should say, you end up with a thicker coating of material when you have the 2-cis, TMV. So by changing or modifying the surface of the TMV, you can affect the coating of material on the surface. Mayo had an interest in looking at other viruses, and the two viruses that he looked at was alfalfa mosaic virus, and also the barley stripes mosaic virus. And when we use a hydrothermal synthesis technique to coat palladium on these viruses, what we found is the AMV didn't look as pretty. So we didn't have pretty pictures. But the BSMV is a real jewel. And as you can see, the particles are uniformly coated, just like TMV. So now we need to understand better what's going on with BSMV, but like TMV, it looks like the first and second coating, perhaps we didn't completely coat the BSMV with a layer of particles with the first coat. And so when we went up to third and higher coatings, you see the size of the coating actually increase with the number of coating cycles. And also, as I said before, the rate constant, the first order reduction rate constant actually increases with a function as a function of the concentration of BSMV. And that's why we actually divided the rate constant by the mass of the biotemplate. So the conclusions from this work, using in situ X-ray absorption spectroscopy and UV-Vis experiments, we were able to do something about the reduction of palladium, at least the kinetics of reduction of palladium on the metal, on the plant virus. And also, using in situ SACs, we can measure the size of these palladium nanoparticles and basically how they evolve over time during the reaction. We're also investigating the coating of BSMV, and it behaves a lot like a TMV. And so we've used the UV-Vis and USACs to compare we're using it and analyzing the data now to compare the BSMV and the TMV in terms of palladium reduction on these two biotemplates. So, now for the last part of my talk, which is particle deposition during drop evaporation. This work was started back in 1996 when I was a young lad at the University of Maryland. And the student who worked with that was Nachi Liu. And later on, when I moved here, Fifi Wijaya, Fei Song, and most recently, Nicole Devlin worked on this problem. And Ms. Wang is now working on the problem, and look forward to her excellent work and future presentations, and of course, the most important thing, publications. Now, so in terms of nanochromatography, which is something that Nicole Devlin was very interested in, up until Nicole, most of the work was done on a single particle size, and under isothermal, where the droplet was calculations and everything was done under isothermal conditions. But she ran into this paper where some researchers looked at the evaporation of a system of 2 particle sizes, 1 micron and 6 micron particles. And what they noticed is the smaller particles tended to go closer to the contact angle than the larger particles. And so if you know the distance between these 2 particles, and of course you know the diameter of the particle, you say something about the contact angle right at the contact line. Now, if you could get such nice separation just from drying a droplet, that would be interesting. So they did some modeling, but they only modeled the fluid flow. They didn't actually look at the particle deposition or anything. So we were very interested in looking at that. Another group looked at 3 different particle sizes, 4 nanometers to 2 micron in size. And once again, the smaller particles were closer to the contact line than the larger particles. So we said, well, let's do some computational modeling of this. First, using isothermal conditions, where you have the drop here, and then you have a gas phase located out here, and the drop is axisymmetric. Then you have your transport equations that all of our grad students and undergrad students have fallen so in love with because they're so cool. I could take this and just keep going around like this because it's such a cool equation. So this is dimensionless form, so we have a couple of dimensionless groups, the Reynolds number, the capillary number, and we also have the stress tensor shown here. And also, so this is the Cauchy equation, or the Cauchy equation shown here, and then down here we have the continuity equation, and solving those you can solve for your velocity in the U and V direction, or the radial direction and the axial direction, and also P, which is the pressure. So you have 3 equations, 3 unknowns. And then you have your series of boundary conditions shown here, and we won't go through those because we're well aware of those. And then for the vapor composition in the vapor phase, out here, above the droplet, we assume that we can look at the approximate concentration and set it equal to 0, and so we have a quasi-static governing equation. The convective diffusion equation, when you bring in the particles, you can have an equation for particle 1 and particle size 2, and so you end up with these 2 equations, Beckley number, and the Beckley number is given by this expression here, some characteristic length scale, which is basically the radius of the droplet and or the radius of the droplet that it makes on the surface. I mean the cross section that it makes on the substrate, and the velocity, some characteristic velocity scale, which is dependent upon the evaporation rate of the droplet from the surface, and then your self-diffusion coefficient, which is computed by the Stokes-Einstein equation for those small little particles. So we can put in the boundary conditions for the particles. We won't go through those either, but there's a boundary condition for the symmetry boundary condition the boundary condition along the liquid-air interface, and then the boundary condition for the deposition of the particle on the substrate. So here are the results. If you do the isothermal simulation, you get flow fields that look something like this, where the liquid is flowing in this direction and then flows to the contact line. Because in our calculation, the contact line is 10. So if you're going to replenish the fluid to the contact line, you have to bring fluid to that contact line. And here are the particles. And what you see is that the large particles accumulate at the edge more than the small particles. This is the large particles here, and you see has an indication that it's around 20 right at the contact line, whereas the smaller particles has a mass of about 6, mass concentration about 6. And if you look at the outside of the droplet, you see the small particles are more on near the contact line, and the inside of the droplet is in this direction, and you see larger particles are not as close to the contact line as the smaller particles. So, the simulations, or using the computer model that we have, there are some problems. And another problem is, if you look at the deposition rate of the particles on the substrate, at time 2.2, this was time 2.28, you see very little particles near the contact line. At 4.04, there are probably a few more particles, but most of the particles deposit right towards the end of the drop drive. So the model, the isothermal model, has problems in terms of calculating the rate at which the particles reach the contact line. So we put in the energy balance equation for non-isothermal system. And in this case, we have the thermal Peckley number, and then the boundary condition is shown here for, let's say, the heat flux across the heat flux that's due to the evaporation at the surface of the liquid. So we also have to take into account that the surface tension now will change because it's a function of temperature, and we use this equation to describe surface tension function of temperature. And also the traction boundary condition, no longer do you just have this term, you have to add the gradient of the surface tension because the surface tension is changing along the interface. So when you do that, you get this Marangoni flow that's shown here. So rather than having a liquid going to the contact line as the drop evaporates, you have this circulating flow within the droplet. And when we do that, the 3 micron particles don't accumulate as fast in the contact line area over here. And so this shows that the particles aren't depositing as quickly because of the Marangoni flow, which is consistent with what we see with the experiments. So with thermal variation, you don't get very rapid deposition of the big particles or particles at the contact line, whereas when you have isothermal conditions where the flow can go directly to the contact line, you can have a very high concentration of particles at the contact line early on. So you have to include the thermal variation in the model. This whole thing about the particles not being able to reach the contact line is due to the fact that the liquid height constrains the large particles from accumulating closer to the contact line. So the small particles can get closer to the contact line. And what I want to show here, well, maybe not. Okay. Oh, there it is. If you can look at the particles, the big particles stop, and the small particles keep going closer to the contact line. So as long as the number of big particles aren't high enough in the layer where the big particles stop, the small particles can go around the big particles or go between the big particles to get to the contact line. Although the big particles can actually arrive at the contact line, if they're in the same, start off in the same proximity as the small particles within the droplet, the big particles will actually migrate to the contact line faster. That's just another static example. So you can have a situation that if the concentration is slightly high, you can get a layer of small particles because as the big particles form, the small particles can go around the big particles to reach the contact line, close to the contact line. The big particles are stuck at some distance away from the contact line. So, and then later on, and once the concentrated big particles gets large enough, so the small particles can't filter through the pore spaces, you can get another layer of very small particles. So we did this, and then I asked the question, so what happens if we have a sessile drop versus a pendant drop? Well, when we did it with the sessile drop, we got this nice accumulation of the small particles near to the contact line, but then you get, some big particles, small particles around here, and this is near the contact line. If you look at pendant drop, number one, the contact line on a macro scale, it looks like it's fixed, but in the micro, okay. So in the micro scale, you get this pendant drop. You get big particles in the center. Sessile drop, you get big and small particles in the center. And so when you model this, you have to include the gravitational effect number. And finally, you get, when you do the simulation, it shows that you get big particles in the center and virtually no small particles in the center. And I've been waiting. I didn't see anything. I'm sorry. Okay, as I told you, I'm going to keep going. So, my future fun, I'm going to continue to have fun doing research, and I guess I should put up the acknowledgments. My collaborators, and I missed Brian and Doris in some of the work we did with the palladium-coated TMV. Sorry about that, Brian. Please don't ask a tough question. And a number of undergrad students have worked on these projects, and the funding sources are people that allow research to go. So with that, you have any questions?
Any questions? Yes.
What was the working fluid they used in the droplet? What was the working fluid for the droplet in the evaporation study?
So, in a lot of cases, it's either water or ethanol.
Thank you for your time.